Let's do a simple but interesting problem related to normal force and on a horizontal surface. So this is the case of a book at rest on table as shown in the picture. A book rests on a table with two legs as shown. The center of mass of the table is shown with a dot, and we have to answer the following. First one is show all possible pairs of action-reaction forces applicable for the system of objects. So we have three objects over here. So we have the book, the table, and the earth or the ground. And we have to show the action-reaction forces. So we know that there are two different type of forces that will be coming into play. One is the force of gravitation between these objects, and other is the normal force between these objects, as we will see in detail when we come to the solution. And we have been told to ignore the force of gravitation between the book and the table. The next is we have to draw a free body diagram for the book and the table, and followed by write the equations for vertical equilibrium for the book and table. So we have to apply Newton's second law. The net force should be zero because the objects are at rest. In the vertical direction, we have to apply the Newton's second law. And once we have done all these things, we have to find the values for all the normal forces applicable. So let's get into it. One more thing, in case you are interested to go into the conceptual explanation for the topic, you can refer to my video mentioned at the bottom. You will find it very useful. So coming to the first part, action-reaction forces to be considered between the pair of objects. How many pairs we have? So let's list down the pairs that we need to consider. So we have the book, and then we have table, and then we have earth or ground. And then again, I'll put them in the same order to be able to identify the pairs. So we have book, table, and earth or ground. Coming to the pairs, how many pairs we have? So from the book perspective, it will be book and table. So one pair between book and earth, second pair. So forces always exist between a pair of objects. So that's why I'm trying to identify how many pairs are there in the picture. So from the table perspective, it will be between table and book, and between table and earth. And from earth perspective, it will be between earth and book, and also between earth and table. As far as the pairs are concerned that need to be considered, I've listed down the pairs over here. So in this column, I have put the pair of the book B and table T, and the second pair is the book B and earth E, and the third pair is between table T and earth E. And we know that there are two types of forces that we need to consider. One is the force of gravitation, and other is the normal force. So we have three pairs and two type of forces between them. So 3 times 2, that will be 6 pairs of forces because it's action and reaction. And these are the 6 pairs of forces which we are going to talk about. So let's go one by one. Force of gravitation. So it's given that between the book and the table, although yes, there will be a force of gravitation applicable, but it is so small that it has to be ignored so that it becomes negligible. So that's why I have kept it no over here. Yeah, there will be a force, but in the question itself, it is given that we don't have to consider that. And since we don't consider that, there is no point in considering either of the forces in the pair. So this is safely completed. Now coming to the normal force between the book and the table. Will there be any normal force? Yeah, because they are in contact, and the book is resting on the table, and therefore the weight of the book is being balanced by the normal force provided by the table. So let's go in detail. So the normal force, yes, it will be applicable. What is the action force and what is the reaction force? So any of the two forces in an action-reaction pair can be considered as action or reaction. So these are interchangeable. So, but we need to follow certain way forward. So I've considered, let's say, the normal force exerted by the table on the book. Yeah. So the normal force has to balance the weight of the object, and weight of the book is mg. Yeah. So with respect to the vertical equilibrium consideration, I'm going to draw the free body diagram a bit later and also the equation. But once we refer to that free body diagram, it's very easy to make out that the normal force by the table on the book will be equal to mg. Yeah, mass of the book times acceleration due to gravity. And since every action force has a reaction force, so there will also be a normal force that will be provided by the book on the table. And that's because that's the action and reaction force. And why it will be equal to mg? Because action and reaction forces are always equal in magnitude. They may be opposite in direction, but they're always equal in magnitude. So this too, NTB and NBT form action-reaction pair, and that's why NBT will be equal to mg. Now let's move to the pair book and Earth. So will there be a force of gravitation applicable? Yes, because Earth will be pulling the book towards it and vice versa. So let's say for convenience over here also, action and reaction forces can be used interchangeably. So let me just call the action force as the force by Earth on the book. That will be equal to the weight of the object, and we know that that is given by mg. Okay. And how about the reaction force? So that will be a force by the book on Earth, and that will be equal to mg. Why? Because action reaction forces, these two pairs are action reaction forces, they're always equal in magnitude, opposite in direction. So magnitude is mg. So how about the normal force between the book and Earth? Now, normal force is always applicable when the two objects are in direct contact. So is the book in contact with Earth? No. And therefore, there will be no normal force between book and Earth, because book is resting on table and table is then in contact with Earth. Now let's focus on the forces applicable between table and Earth. First of all, will there be a force of gravitation? Yes, it will be. So let's see what are the forces. I have considered the action force as force by Earth on the table, and we know that that is equal to the weight of the table, and that is equal to mg, capital Mg. And how about the reaction force in this pair? That will be force by the table on Earth. That will be, because it's an action and reaction pair, these two forces are action and reaction. The magnitude is the same, direction is opposite. So therefore, FTE will also be equal to mg. So how about the last pair? So between the table and Earth, do we have the normal force? The answer should be yes, because they are in contact with each other. Yeah. So let's see what are those forces. So the normal force by Earth on the table. Now this, I've written it as m plus mg. This is because of the condition of vertical equilibrium. As soon as we draw the free body diagram for the table and we see the equation for the vertical equilibrium, then we will come to the conclusion that NET will be equal to m plus m times g. Now, how about the second force in the pair? That's normal force by the table on Earth. Because these two are action-reaction forces, therefore they have to have the same magnitude, opposite in direction. So magnitude, therefore, will be equal to m plus m times g. As I mentioned, these are action-reaction forces. So I hope you have a complete picture about all the kind of forces that are applicable and to be considered between the pair of objects given in the problem. So let's now focus on the free body diagram for the book. So I've drawn the book. That's the only object we need to focus on and see all the forces which are acting on the book. So the first force that we can consider is the force by Earth on the book. That is the weight of the object, and that is given by mg. So that will be, of course, all the forces will be acting on the center of mass of the book, which is identified with a dot. And the weight will be acting vertically downwards towards the center of the Earth. So weight equals to mg. And how about any upward forces acting on the book? Yes, there will be. There will be a normal force. First of all, why there has to be upward force? Because it's given that the book is at rest. Since there is no motion, so the net force in the vertical direction has to be zero, which is possible only when there is one more force acting in the upward direction, which has a magnitude equal to the weight of the object. And that force, we call it as the normal force. Normal force by the table, and normal force is always by the surface which is in immediate contact. Yeah, by the table on the book will be equal to mg. So we have two equal and opposite forces acting on the book, and therefore, since the weight of the book is being balanced by the normal force on the book, therefore the book is in equilibrium. And it is only for interest I have shown some of the arrows to indicate with a dotted line, and there is a reason for that. Although it's not a part of free body diagram. Say, for example, this force. All I'm trying to show is, as much as possible. From the free body diagram perspective, it is not important. You can skip the understanding on the dotted line. But to have a full understanding of the picture, you need to understand that this is a pair of forces, normal forces. So this will be the normal force by the book on the table, and that will be equal to mg. And similarly, the other pair of forces, they are also action and reaction pair. So this will be force by the book on the earth, and that will also be equal to mg. So since if you see the dotted forces, these forces are acting, these forces are not acting on the book, and that's the reason they are not a part of free body diagram. I just captured them for the sake of complete understanding. Yeah, as you see, this force is a force on the table, and this force is a force on Earth. Whereas what we are doing right now is the free body diagram for the book, and that's the reason these dotted forces are not part of the free body diagram. Now coming to the equilibrium equation. So we know that since the book is at rest, therefore there is no net force on the book, and therefore from Newton's second law, sum total of all the forces acting on the object should be equal to 0. So we have only two forces, NTB plus FEB. So when these two forces are vectorially added, they should give is 0. Okay. In terms of the magnitude, this is possible for the two vectors to meet this condition. It is possible only in one case where the magnitude of the upward force equal to the magnitude of the downward force. So NTB should be equal to FEB. Yeah? And we know that FEB equals to the weight, and that is equal to mg. So eventually, the upward force, which is the normal force by the table on the book, has to be equal to the force exerted by Earth on the book, and that is nothing but weight of the object equal to mg. Let's now focus on the free body diagram for the table. So keep into consideration only the forces acting on the table. So there will be some forces in the upward direction and there will be some forces in the downward direction. Let's analyze them one by one. First of all, ignore all the dotted arrows because they are not actually part of the free body diagram of the table. So focus only on the continuous arrows. Yeah. So center of mass of the table, all the forces are all the forces which I have drawn over here, this and this, is at the center of the mass. So these two centers actually, you can understand them as one point only because I had to write the names of the forces, so I shown them separately. But for all practical understanding, it's only these forces, for example, are acting at the center of mass, and there can be only one center of mass of the object. So let's see all the forces which are acting on the table in the downward direction. So first force will be the force by Earth on the table. That is nothing but the weight of the object, and weight of the object is given by capital M times G. So that is acting at the center of mass, pointing in the downward direction, vertically down, actually towards the center of Earth. Now, is there any other force acting in the downward direction? Yes, you can see one more, which is over here. That's the normal force, as I explained in the previous picture. Normal force by the book. I have not shown any book in this picture because it's a free body diagram for the table. So normal force by the book on the table. And that from the previous picture, keeping in view the vertical equilibrium for the book, we have seen that NBT equals to mg. So these are the two forces acting in the down direction. And what are the forces acting in the vertically upward direction? So I've drawn them over here, this and also this. So more about this I'm going to explain when I come to the equation for vertical equilibrium. But from the picture perspective, you see that this is a normal force by Earth on the table. Yeah. So that will be given by some number, which I'm going to talk about a bit later. But important to understand that the normal force by Earth on the table will be split on the available number of legs of the table. So if there are two legs, as I have shown in this picture, so the normal force will be equally normal force by Earth on the table will be equally divided between this and also between this. So that's going to be exerted on the surfaces in contact, and it is the legs of the table which are in contact. And therefore, these two forces have been shown acting on the surface in contact, whereas the other two forces, I have shown them acting on the center of mass of the table. So this is for a clear representation, clear understanding on the point of application of the force. Now coming to how do we apply the Newton's second law? It's given that table is at rest. That means there is no net force acting on the table, which means vector sum of all the forces acting on the table, that is NET plus FET and the NBT, the three forces that I mentioned. These three forces, when added vectorially, they should give a zero. Yeah. So yeah, and this equation is the same as the above equation. I think I have written it by mistake. Now, for the three vectors to satisfy the condition that their vector sum is equal to zero, that is possible only when this condition is met. That means vertically upward force magnitude will be equal to the sum of the magnitudes of the vertically downward forces. So, which means NET should be equal to FET, which is mg, capital MG, and NBT, which is small mg. Yeah, because from the earlier equilibrium condition and also the free body diagram for the book, we have seen NBT equal to NTB equal to mg, and therefore the condition is NET should be equal to m plus m times g. And as I mentioned, the force NET, that's normal force by the ground on the table, which is over here, that will be equally split across the number of available legs. So on one leg, you will have NET divided by 2, which will be m plus m times g over 2. And similar force on the other leg also. So before I forget, let me focus on the dotted arrows also. So as I mentioned in a free body diagram, the dotted arrows are not a part of the free body diagram because those are not the forces acting on the table. So, but for the sake of completeness of the understanding of the action-reaction pairs, let's identify them clearly. So this is one pair of action and reaction. So this is NBT. So therefore, this has to be NTB, and the magnitude, of course, will be same in the pair. And similarly, this is one pair. So this is FET, and therefore this has to be FTE with equal magnitude. And similarly, this one is a pair, and this is NET by 2. So therefore, this should be equal to NTE over 2. And similarly, this is a pair. The continuous arrow is NET over 2, and therefore this one should be NTE over 2. So let's revisit if all the parts have been answered. We have listed all the possible pairs of action-reaction forces. They included normal and also gravitational forces. Then we have also drawn the free body diagram. We have also written the equations for the vertical equilibrium for the book and the table. And lastly, we have also derived the values for all the normal forces applicable. For part 4, to be clear, so normal force by the table on the book will be equal to the normal force by the book on the table, and that will be equal to mg. Okay, whatever value of m is given, based on that you can find out mg. And normal force by Earth on the table will be equal to normal force by table on Earth, and that will be equal to m plus m times g. So that makes the solution complete. Thank you for watching. Please like, subscribe, and share the video. If possible, please drop the comments as well. Thank you.